We saw yesterday when we looked at confidence intervals that as to decrease the confidence interval, one of two things must happen. Either you must increase the sample size or you must decrease the confidence level. That's because both of those, the sample size and the confidence level, are a part of the margin of error, which we see if we look at the formula. Yesterday's formula was a little more general. Today we're going to get a little more specific. The formula for calculating a confidence interval is statistic plus or minus, and you end up doing both, the margin of error, which is the critical value, which is formed by looking at the confidence level, times the standard deviation of the statistic. This formula is exactly as you see it written here with a little neater handwriting, is exactly how it's written on the AP formula sheet. We have more specific formulas for dealing with p-hat and for x-bar. Those specifically are not on the formula sheet. However, knowing this general formula, as long as you know what each piece means, then you should be able to determine what to replace it with to make the more specific formula. Okay, so to reduce the margin of error, and I've already mentioned this a little bit, one way to do it is to decrease the confidence level. Obviously, there's a drawback there because you're just not as confident in your results. The other way to reduce the margin of error is to reduce the standard deviation of the statistic. And the only way to really do that we can control is if we increase the sample size. Now you might think, well, there's not any drawbacks to increasing the sample size, but there is. Because larger samples are more costly and more time consuming. So if you increase the sample size, it might cost your company more to take the sample. It's going to take you longer to get all your data, take you longer to analyze all of your data, etc. So there are drawbacks. Okay, one thing we need to make sure that we do is we need to use our confidence intervals wisely. We need to always make sure that we have the information needed to do the confidence intervals before we start. And there are 3 conditions that must always be met to do a confidence interval. And these conditions are really important to know because they're needed for many things that we're going to do from here on out. Many of these inference procedures that we're going to use for the rest of the year require these conditions to be met. So the first condition is that it must be random. And by random we mean that the sample must be taken using a random method. Secondly, it must be normal. And before I go on, let me say why it must be random. If it's not random, if our sample's not taken in a random manner, then our data could be biased. And if our data is biased, then we have no foundations for saying that our results are true or that they would reflect accurately upon the population. Because if the data is not an accurate representation of the population, then our information is not going to be either. And you might say, well, what about the whole sampling variability that we talked about in the last chapter, where all samples differ a little bit? Well, our other methods and our other conditions make up for sampling variability, but they do not make up for bias. Okay, so normal, the sampling distribution, of our statistic must be normal. And the reason behind that is because everything we do, even the idea about confidence intervals and the idea that within 2 standard deviations of the mean, there's about 95% of our data, and knowing that the mean of the sampling distribution is in the middle of the data, all that's based on the fact that it's normal. So if this condition is violated, then we don't have any methods for taking our methods for making these calculations, because we wouldn't know anything about the sample from which it came, or the population. So, number 3, independent. Okay, individual observations must be independent. Okay, or in the case of sampling without replacement, because that makes it not independent when we sample without replacement, the 10% condition must apply. Okay, and remember that the 10% condition says that our population needs to be at least 10% more than our sample size. Our sample size must be less than or equal to 1/10 of our population size. So these are our 3 conditions. And the reason that the independent one is so important is because if it's not independent, then when we collect our sample, every time we take one of our pieces for our sample, that's going to change the probability of us picking something else. It's going to change our whole population. And it's going to change the standard deviation as we go through it. If it's changing the standard deviation as we go, well then when we go to use the standard deviation in the formula, how do we know which one to use? So we need them either to be independent or for the sample size to be so much smaller than the population that it's not really affected. That the change in all of the population every time you pull one is so minimal that the standard deviation is not affected. Okay, let's specifically talk about constructing a confidence interval for a proportion. So using p-hat to estimate p. We always have to check the 3 conditions, and the conditions themselves are the same, but how we check them differs for p-hat versus x-bar. So 1, random. If it's random, it will say so in the problem. You will need a reason to believe that it's random, or it will need to say random sample, etc. If you have no idea how they collected their sample, then you can't say that it's random and that condition's not met. 2, normal. Remember from last chapter that we have a method for checking whether or not the sampling distribution of p-hat is normal. And that's to say that n times p must be greater than or equal to 10, and n times 1 minus p must be greater than or equal to 10. And hopefully you're looking at this formula and you're going, but wait a minute, we're estimating p, so at the moment we don't know what that is. Well, for the purpose of this, we can use p-hat. And we say it's normal if n times p-hat is greater than or equal to 10, and n times 1 minus p-hat is greater than or equal to 10. And finally, independent. You must either be able to say that they are independent or that the 10% condition applies. Be very wary of problems. Like, always make sure you check the conditions for a problem. And if there's a problem where all they ask you to do is check the conditions, be aware that sometimes they may be wanting you to say which one's not met. So don't assume that they're always going to give you problems where the conditions are met. So for example, let's look at this. Miss Class wants to construct a confidence interval for the proportion of pennies more than 10 years old in their collection. Their sample had 57 pennies more than 10 years old and 45 that were at most 10 years old. Okay, so that's important information to remember. 57 that were more than 10 years old, 45 that were at most 10 years old. Check that the conditions for constructing a confidence interval for P are met. So 1 would be random. They do not tell us how they collected their sample. They do not mention it at all. Because they don't say anything about it, I have no proof that this was a random sample. So I can't say that this condition was met. So number 2 would be normal. And this one, no. Okay, so we would say N, which I would have to say 57 plus 45 to get the total sample size, which is 102. So 102 times P, which would be 57 over 102. Well, that's equal to 57, which is greater than or equal to 10. And then I have to say 102 times 1 minus P. Well, that's just going to be the number of pennies that were at most 10 years old. Turn that into a proportion, and that's going to give me 45, which is greater than or equal to 10. So this condition is met. And then 3 would be independent. I'm going to assume that they were sampled without replacement. That they would have collected their pennies the same way we collected our pennies in the last chapter and pulled out 1 at a time or 2 at a time. And so when that's the case, their population would have to meet the 10% condition. But they have 102 pennies that they've sampled. We don't know anything about their collection. I mean, if they're like us, our collection was only 500 pennies, so that would not meet the 10% condition. So since we don't know anything, we have to say no. So since we've talked about checking the conditions, let's break down that formula, that statistic plus or minus critical value times the standard deviation of the statistic, into an actual formula for p hat and to estimate p. So my confidence level, if I'm talking about my statistic, well, that means I'm talking about p hat, because that's the statistic I calculated for my sample, plus or minus, okay? The critical value has a symbol called Z star, and we'll talk about that in a second. And then I want the standard deviation of the statistic. Well, the standard deviation of P is the square root of P times 1 minus P all over N. But I have a problem. And you might say, oh, well, we don't know P. That's our problem again. Well, we may not know P, but we know a good estimator for P, and that would be p hat. So if I just turn these into p hat, I can use that to calculate my standard deviation. Okay, when we have to plug a statistic in for a proportion, or not a proportion, a statistic in for a parameter, in order to calculate the standard deviation like we did right here, that is no longer called standard deviation. What it is actually called is standard error. So standard error is when you plug in a statistic, which is from sample data, instead of a parameter to find standard deviation. Okay, so our formula for standard error then is the square root of p hat times 1 minus p hat all over n. Okay, this is interpreted very similar to the standard deviation. It is on average how far away from the actual value our predicted value is. So how far away from p, which is the mean of the sampling distribution of p hat, is p hat. So on average, how far away from the actual value is the one that we calculated from our sample. This formula not on the AP formula sheet. However, they do give you on the formula sheet the standard deviation of p hat, which is just this right here, but with p instead of p hat. So hopefully you will be able to see that one and say, oh, I don't have p, I only have p hat. I should plug p hat in for p. Okay, let's talk about the critical value. Hopefully you've noticed that it is a Z star. Okay, and you say, well, why is it a Z star? Or why do they use Z? That's because what this tells us is how many standard deviations away from the mean I would expect this to be. Okay, and then when I multiply it by the standard deviation, that gives me the actual units to add to my statistic. So this is based off of Z-scores. That's why it's called Z star. The Z star is there. The Z star is there in order to help us remember that this is not calculated the same way as Z-score is. It's actually calculated in reverse. And what I mean by that is, let's say that we want a 95% confidence interval. Okay, this is our confidence level, and it's what Z-star is based off of. That means I am looking for the middle 95% of my data. Okay, remember that normal curves are symmetric. So I have 5% left that is split between here and here. And so that 5% has to be divided in 2, which makes this 0.025 or 2.5%, and that makes this 0.025 or 2.5%. The way that I can find my critical value is to either use Table A, and I'm going to look inside the body of Table A for a percentage that is close to 0.025. Okay? My other option is that I could look for this Z-score right here, in which case all of this area would be 0.975. I could look for that value in my Table A. And I need to look then to the sides and the top to see what Z-score goes with it. In this case, with a 95%, it's going to be 1.96. Okay? Because they're symmetric, this Z-score would be negative 1.96. See that they are the same number. One's negative and one's positive. Okay, for our Z-star value, we don't look at the sign. We just take the positive value because that's what this plus or minus up here does. It moves it one way for the positive Z-score and one way for the negative Z-score. So that's how we find it. If you're interested in finding it on the calculator, if you hit second distribution and you type in inverse norm, and then all you have to do inside the parentheses is either enter in 0.025 or enter in 0.975, and it will give you your Z-star value. Okay, you might be saying, 1.96, I thought 95% of our data was within 2 standard deviations. Why is this not a 2? Okay, well, that rule is an estimate. So it's really about 95% of our data is within 2 standard deviations. So this gives us the actual value, not the estimate. Okay, so if I look at this example, it says students in an AP statistics class want to estimate the proportion of pennies in circulation that are more than 10 years old. To do this, they gathered all the pennies they had in their pockets or purses, and overall 57 of the 102 pennies they have are more than 10 years old. So identify the population. Well, the population is just going to be this proportion of pennies in circulation. Well, not the proportion of pennies. The proportion would be our parameter. It's going to be the pennies in circulation as our population. Okay? The parameter is going to be what we're interested in finding out about the population. And that's going to be this proportion of pennies in circulation that are more than 10 years old. That's our parameter. So then I check my conditions. I can say that it's random because they're gathering all the pennies they had in their pockets or purses. They're not picking out specific ones. They're taking all the pennies that they have to make their sample. We can assume that's random because we can assume that those pennies came from various places, who then got the pennies from various places, who got the pennies from various places. So there's nothing saying that these pennies were systematically chosen. Okay, so then to do the normal condition, it's really the same as it was earlier because we have the same proportion and the same sample size. So you would have to say 102 times 57 over 102. And that's going to give us 57, which is greater than or equal to 10. And then I have to say 102 times 45 over 102, which is 45, which is greater than or equal to 10. And then I need to check the independent condition. Okay, they are sampling without replacement. But here we can say that because their population is the proportion of all pennies in circulation, that there are more than 1,020 pennies in circulation. Because 10 times 102 is just 1,020. There are more pennies than that in circulation, so we can say it's independent. So then I need to construct my confidence interval. And to do that, I use my formula. So I say the statistic, which is 57 over 102, plus or minus my z-star value. Okay, so I would plug that in and find the z-star value. So I would, with a 99% confidence level, that's the middle 99%. Which means that the area that I could plug in my calculator, this right here has to be 0.5%, so 0.005, which means this right here has to be the 0.5%, 0.005. So I could look up 0.995, or I could look up 0.005. Either one works. When I do that, I get 2.576, or 2.58 if you're using Table A. Then I do the square root of 57 over 102, which is p hat, times 1 minus 57 over 102, all over 102. Okay, and when I multiply that all out, I get the interval of 0.432 to 0.686. So, to interpret the interval in context, this is my interval, and I would say that we are 99, from this right here, % confident that the interval from 0.432 to 0.686 captures the true proportion of pennies in circulation that are more than 10 years old. Okay. Then this question says, is it possible that more than 60% of pennies in circulation are more than 10 years old? And we would say yes, that's totally possible because 0.6 is well inside this interval. Anything that is in this interval, it is plausible to us that that would be the right value for the proportion.